Mutlu here. He's both with SAGE and Forest and Wildlife Ecology. And I will turn it over to you, John. Anything else?
Thank you so much.
Thank you. Appreciate it.
Hi, everybody. My name is Mutlu. I'm an associate professor in a joint appointment between Forestry Department and SAGE in the Nelson Institute. I'm a geographer by training, and I do a lot of remote sensing analysis. So some of the work that you'll be seeing over here is a result of sort of remote sensing analysis. Sorry, let me take this off. It keeps ringing. Remote sensing analysis that we're doing. And just to provide a little bit of sort of historical context, so this work actually has its origin about 5 years ago when I was working with my PhD student back then, Yang Hui, who was developing crop yield models using remotely sensed inputs and data assimilation models. And one day she approached me and she said, well, these models that we're developing for crop yields could actually be applied in forested environments as well. But her PhD work did not sort of fit into that, and then she graduated and I dropped it. And back in March we had the SAGE CCR lightning talks. I'm like, this is the kind of topic that actually perfectly fits that. So I brought it back, and since then we've been working on it on and off. So some of it may feel a little bit preliminary, so this is not published work yet. So our goal is to sort of complete this work and go towards publication. But my hope is that it generates excitement and discussion. It may feel a little short because of the preliminary nature of the work. So what we're trying to do over here is quantifying the carbon potential of woodlands in agricultural settings, and I'm going to describe what that means in a second. So just to sort of set this stage over here, so there is very strong interest in carbon farming, so that some of you may be familiar with, that both public and increasingly private entities are paying farmers to do what's called carbon farming, where they're actually implementing regenerative practices to keep the soil full of carbon, but as well as accumulate carbon from the atmosphere. So almost like a reverse sort of climate change in a sense, at least one way of doing it. Now, in my view, there is a neglected part of this equation that has to do with the forested lots in agricultural areas, and I'll describe that in a second. Now, it turns out, believe it or not, but in the Midwestern United States, defined as sort of a number of states around us over here, the forested area in agricultural plots is actually twice as much as the forest areas in pure forested lots, if you add up all the sort of little forested pieces. So one of the things that we're trying to quantify is that how does that sort of small woodlands in the back part of the sort of 80-acre cornfield mean with respect to sort of carbon sequestration and carbon accumulation? And can we quantify the amount of biomass and carbon sequestration in those areas? So that's the question that we're trying to answer. So with respect to this question of what is a agricultural forested land, I call them, it may be in the next slide, but this will be 100% forested landscape. So there's a 60%, 40%, 20%. I am particularly talking about those kind of landscapes. And if you look around us, if you drive around, our landscape is full of that, and then full of these as well. But these are the ones that we're doing sort of co-work, if you will, both growing carbon, if you will, but also doing lots of agricultural activities. So it is these what I call farm woodlands that we're particularly interested in. So how do we know there's twice as much woodland in those agricultural plots? So what we can do is we can actually take parcel data, which are somewhat publicly available across those states, and then eliminate all the parcels in urban areas, residential areas, industrial areas, and you're left with urban parcels. These are land ownership boundaries. And there are about 20 million of them, so about 18 to 20 million of them across this landscape. And then each state has slightly different because of how they're settled and how the land was sort of demarcated or divided, if you will. But if you can take all of those parcels and simply eliminate all those really tiny ones, eliminate all the residential and urban areas, you're left with those urban parcels. And then you can intersect that with a high resolution, highly accurate land cover map, and then simply tally the results. So you can actually identify those forested plots defined as greater than 95% fraction of forest, and then simply count the areas of those against all of the other ones that have some agricultural activity in them. And if you do that math, it's about twice as much. So data is all there. and then we're actually making this publicly available. This is all derived from publicly available data. So if you focus on Wisconsin, and it turns out that if you eliminate all the other land cover types like wetlands and water and urban areas, this is the kind of sort of histogram distribution you would see in terms of fractions of forested lands and cultivated lands. And what's interesting over here is that if you look at the forested areas, we have lots of plots that are pure forest. We have lots of plots non-forest, right? This is southern Wisconsin, this is northern Wisconsin right here, and we have a lot of in between, and it's that in between that we're tallying up. And if you look at the croplands, it's exactly opposite, and it turns out that those are actually mirror, images of each other, right? So this is 100% forested land is actually 0 plus 10% cropland, so on and so forth. So the rest of the talk is going to be examples from Wisconsin, as the sort of preliminary part of this work. So going back to this question, how do we try to answer this question? So we have sort of two parallel approaches. The left one is the forest carbon computation part, and the right one is the soil carbon computation part. Now this one is entirely focused on estimating above ground biomass. And from above ground biomass, we can go to carbon, and then we can see, how many sort of, tons of carbon that is sitting out there on those little agricultural plots with lots of, little forested plots in agricultural areas. So what we do is we identify all the forest pixels, using a land cover map, and then we develop a model to estimate forest above ground biomass in forested areas using JEDI LiDAR-derived above ground biomass, which is a product that you can download. It's a publicly available product, but it's a footprint product. And then, use that and bunch of predictor features from remote sensing and environmental variants, and then apply that model to make wall-to-wall maps of above-ground biomass of those forested areas, and then go through a validation process. Now, on the soil carbon side, we're actually not trying to figure out how much soil, carbon is in the soil, but rather how much carbon can you accumulate through regenerative practices? Now, it turns out that that's actually a pretty difficult question to answer. So we've taken a slightly easier approach, an empirical approach where we've reviewed over 80 papers, and we simply looked at, here's a plot of land that they did an intensive study and said, this was the accumulation potential. Here is another study. Roughly about 83 papers. And then, under these practices, no-till and cover crop practices, and then we can sort of read numbers from that literature and then maybe use that as sort of paint-by-number idea. Now, I understand that that's a crude approach, but it's a starting point because it's a pretty complicated problem to solve, in my opinion. So then produce estimates of potential carbon accrual in soil. And combine the two data sets for scenario analysis, and then we're going to look at a few parsons. So assumptions, and then you may agree or disagree with these assumptions, and some of these are strong assumptions, so I'm actually looking for your feedback here. But at this first stage, grasslands are completely ignored, even though they are sort of perennial landscapes, and we have a lot of them on this landscape. We've sort of ignored them for now. Now, carbon accumulation in soil as a result of crop growth is completely ignored. Now, we grow lots of annuals, like corn, soybean, wheat, etc., on these landscapes. Some of them lead to removal of carbon. Some of them lead to accumulation of carbon in the soil, but we go through a crop rotation. And that part over here, whether they're accumulating or depleting because of crop rotation, is completely ignored for now. But we can go back to that. There are publications to perhaps better constrain that. Carbon accumulation potential in the soil is highly site-specific. That needs work. That's what I said earlier. And then only above ground biomass is considered for now. Carbon emissions following forest removal are only from tree biomass. So there is sort of soil-related emissions when disturbance occurred. So that part is sort of ignored, if you will. Carbon sequestration by trees on an annual basis frozen. So those trees are on the landscape as of 2020. So they have a certain carbon accumulation sort of rate that they've locked in. But they are also growing. So we're sort of ignoring how much they're growing and accumulating carbon on an annual basis. And for now, the question focuses on the relationship between carbon accumulation due to conservation practices and carbon stored in woodlands as a sort of frozen in sort of circa 2020. So if you buy all of those, right, all of those assumptions, so let me talk a little bit about this part over here. So as I said earlier, what we've done is that we've taken sort of JEDI observations. If you're not familiar with JEDI, it's a instrument that is on the space station. And then what it does is that it provides footprint-based forest, it's a full waveform LiDAR, and it provides both forest height and forest biomass estimations. So this is a publicly available data set that you can actually go ahead and download. You can download individual footprints, or you can also download gridded versions of these. So what we're doing over here is that we're actually using JEDI derived above ground biomass as the training data, as our Y variable. And we have a number of X variables that we're going to try to predict that above ground biomass. Now, how do they drive? Because we actually start with the above ground biomass data that is coming from JEDI. So this is actually a slide from NASA, and there's the publication right there. And what they do is they divide the Earth into sort of different ecosystems and growing regions, and they're using sort of particular allometric equations in those regions to go from height and other sort of forest profile metrics to above ground biomass. Now, you may say, well, you're already starting with a bad data. Well, maybe yes, maybe no, but this is the best data available. We have literally millions of data points for training purposes. So we take that data, and this is what that data looks like. So those are JEDI cross tracks, and then some of them are repeat cross tracks, so on and so forth. So this is in units of above ground biomass.
Would it help to turn this light off? Does that make it?
Yes.
Absolutely.
Yes.
Okay. I appreciate that, yeah. So then, our goal is to go back to if I can go back to here, our goal is to take this data and then train it based on those footprints and make a wall-to-wall map. So what do we have in between, in the gaps? Well, we have a lot of remotely sensed inputs. We have spectral data, we have vegetation indices, we have SAR data, so we have environmental covariance, etc. So these are all the inputs that we can use to make the prediction. So there are about 120 inputs if you look at all the derivative variables. And what happens is all of those come and then go into a machine learning algorithm, in this case, ensemble machine learning algorithm, random forest and a bunch of other regression models. And then we predict a sort of forest above ground biomass. So those were the footprints I showed earlier, and this would be a forested plot, and this would be the kind of sort of predictions that you would make. Now, these results suggest that with those covariance and remote sensing inputs, we can at least recreate what JEDI was producing, meaning fill the gaps. There is still the question of how accurate JEDI is, and then that publication over there talks about that, but at least we can recreate what above ground biomass is coming from JEDI observations and models. Okay, so next step over here, of course, to validate this with a sort of independent data set. And when I say recreate JEDI observations, we can hold certain percentage of the training data and compare our predictions, and then we do sort of root mean square, about 20% error, if you like. Right? So I think we are able to recreate JEDI observations wall to wall. Once again, there is the question of how accurate JEDI observations are. On the soil side, so as I said earlier, we're taking more of a sort of empirical approach, if you will. So we've reviewed over 80 papers, and what we found is that if you focus only on no-till practice, and we're only focused on two practices, no-till and cover crops, and those are two regenerative practices that have been proposed and have been shown to be effective. And what you're seeing is about 1.24, 1.25, tons of hectare carbon equivalent that you would gain on a sort of an annual basis, if you will. And then here is the number right there, and there is some distribution around that. That's for no-till, and it turns out that cover crops actually have a very similar number, slightly higher, but it's a sort of very similar number. So one of the things that you could do is maybe perhaps paint by numbers, right? So you can go to an agricultural plot that has forested areas in it, and you can say if, in a scenario, if you implemented these scenarios, these regenerative scenarios, these are the potentials that you could accumulate. Now, the carbon accumulation is not very easy. So this is sort of, once again, a paint by numbers, so we need more data and more sort of collaborations to improve those numbers. But this is a starting point in my opinion. So if we take all of those and then combine them together, we could get estimates like these. So what I'm going to show is I'm going to show you two examples of two plots with different levels of agriculture and forest in them. And the sort of red colors are colors of carbon in the soil. And then here's the agriculture part of the landscape. And then, and this is exactly the landscape that I'm talking about, that is dotted in our neighborhood over here. And then the green examples are for the forested areas. So in this particular example, so the forested part was about 70 tons per hectare in terms of above ground biomass. Now, if you convert it to carbon, take half of it, and then convert it to CO2 equivalent, that would give you about 117 tons per hectare CO2 equivalent. Now, if you take the soil part, and then let's combine those two numbers that I talked about earlier, cover crop and the no-till part, and then add 2.5 tons per hectare carbon equivalent. And then there's 42 hectares of forest over, agriculture over here. So at 19 hectares of forest, which covers this part, it would take about 20 plus years of continuous regenerative practices to meet the carbon equivalent of what's forested on that landscape. And then you can play all sorts of games. If the forest is higher, that would be much longer. So why is that important? Well, that's important because one of the things that's happening in the landscape is that those forests are actually slowly disappearing, mostly because of harvest and agricultural expansion. So one of the questions that we're trying to answer over here is that if this plot was converted to agriculture fully, those would be the sort of arithmetic that you would have to do. At least let's call it the back of the envelope arithmetic that you would have to do, that you would have to implement those regenerative practices if you choose to. And then you've got to do it for 20 years to get to what that forest was contributing, if you will. Now let's take another example. In this case, the forest is a much smaller component. In this case, I believe it's about 5 hectares. So in this case, right, it's about 3 years because a larger agricultural area, it's contributing more. Using those same numbers, you would get there in about 3 years. What does that mean? Does that mean that we could actually go in and remove that forest? Is that a permission to do so? That's not necessarily my point over here. My point over here is that there is a diminishing returns as the forest within that sort of agricultural landscapes becomes smaller and smaller. So, from that perspective, on average across all rural parcels identified here, it would take about 17 plus or minus 5 years to sequester enough carbon in agricultural soils to match forest contribution. So if you were to do a scenario analysis, right, if you were to sort of remove all that forest and then turn it into agricultural plots, right, you would have to practice in every plot for 17 plus years to get to what you would have lost. Obviously, this is highly dependent on the amount of woodlands and their biomass, age, size, distribution, etc. in agricultural parcels. Our preliminary work suggests that woodlands with less than 3 hectares are not prime targets, right? And in some locations with forests located in more organic soils, this could be even longer. And then there are diminishing returns in soils with smaller regenerative or carbon sequestration potential. And I'm particularly talking about sandy soils, areas where that 2.5 number that I showed earlier wouldn't necessarily apply. That was an average across sort of many studies under many different soil conditions. But some of them are much smaller, some of them are slightly higher. Now, another way of looking at these results is that, well, is it possible to use results like these to determine the optimum configuration of landscapes? Because we're always trying to figure out, should I, leave this part of the landscape alone for forest for the next 20 years? Or should I be removing, expanding forest, etc.? So perhaps we could try to identify or answer some of those questions. For example, is it possible to remove, what I call enough forest for agricultural activities? or plant perennial grass or forest areas in harmony with agricultural activities. Now I call this in harmony, and I thought about that word for a while, but I think it's the right word because agriculture is not going away. I don't think anytime soon. I mean, if you look at our landscape, agriculture is actually expanding. In fact, some of the work that is coming out of SAGE is showing that agricultural areas are actually expanding, they're getting bigger. Not so much on the forested lands, although they are disappearing as well, mostly on grasslands, but I don't think agriculture is going away anytime soon. So the idea is going to be sort of how do we do this in harmony with agriculture. So, conclusions. So forests and agricultural plots, in my opinion, play an important role in carbon sequestration and preservation in Midwest agricultural landscapes. So while agricultural soils have a strong potential to accumulate carbon, this is highly variable, and it may require strong and steady commitments from farmers. That is, I don't think there's free lunch where you do a regenerative practice for 3 years and then you go back to what you were doing in the past, because you would completely lose almost all of the sort of gains that you would have gotten in those 3 years. Forests greater than 5 hectares should be preserved. That's just sort of opinion that is coming out of this, but there's a high uncertainty around that. And of course, forests play other important ecosystem services, right? Even though the permission to remove forests, if you will, doesn't necessarily mean that it should be removed, because there are lots of other ecosystem services, from biodiversity to water quality, etc. They play an important role, and there's a lot of research on that out there. So what are our next steps? So funding, go get some funding to expand that research, and if you know anything about that, let me know. All right, so collaboration with various groups, hence this talk. So, when I first submitted this abstract, I was actually, I regretted the minute I submitted it, because, I knew that it was preliminary work, and that I was, going to show some examples. But at the same time, I did, I was excited about the sort of the feedback that I would get. We need to do a better job, improve forest carbon estimates, include things like how much annually these forests are increasing their carbon accumulation. Improve soil sequestration potential, go from static numbers that I showed to more dynamic numbers, but I think that's a difficult question to answer. And I'm already reaching out to a couple of my colleagues in the soils department. They have lots of really good observations in Wisconsin, so maybe that's where we can start. And then go from there to scale this to all of Midwestern states. So that's a sort of fast and sort of a preliminary work for me. Thank you.
Thank you very much. All right, really nice talk. We do have some time, of course, for questions. So, does anyone have a question for Mutlu?
Yeah, thanks a lot. That was a really interesting talk. I was curious about your carbon estimates of the forest lands, and if the sort of shape of those forested lands had anything to do with how much carbon equivalent you estimated. I think specifically I'm thinking about, if one of those forests maybe has more edge area against a farmland versus like an internal forest, does that make a difference?
I don't know the answer. All of the estimates are on a per unit area basis, so whether it's a one S-shaped forest, single trees, or 5 rows of trees versus a half, east or west half, I don't know the answer. I think it's an interesting question. There's lots of research on the water side of those things that you may be familiar with. Landscape shape really affects how much runoff you get, et cetera, et cetera. I suspect that there is effect, but I don't know the answer.
On a related note, I wonder if you could include some sort of parameter for erosion control. If you could say, based on the shape of the forest or where it is, if you think it's storing more carbon because it's stopping erosion or something like that.
Yes, and it turns out that at least in some cases, some of the forests are there because of those. They were actually intentionally left there. And like I said, I didn't include anything about what happens if that forest is removed, the additional sort of externalities, if you will. But yeah, I think that should be included at some point. That you don't just lose the biomass, right? You lose more than that.
Yeah. If anything, this is additional information that encourages maybe some sort of policy specifically for erosion control. So in addition to the erosion control, you're also conserving a certain amount of carbon or, you know, like offsetting some of the agricultural processes.
Exactly.
I have a question more about the soil stuff. I know you preface this by saying that's more of the like preliminary stuff, but I'm curious with the your no-till estimates, what soil depth are you sort of assuming for?
20 centimeters. Yeah, which is, I think, typical.
Yeah, with no-till though, I feel like there's a lot of literature that suggests that you might have gains, probably in the ballpark of what you're seeing at the surface, but you might also have simultaneous losses of depth that can offset. So like, there's a lot of skepticism about actual realized gains in no-till.
Fully agreed, and all of those studies were actually, I think all of them look at the sort of top, I think 20 or 30 centimeters, but I agree. That's what I meant by messy earlier. That, I'm looking for ways to improve that, and my colleagues in the soil department, I think, have really good ideas about that. The problem is, you know, they do a really good job in location-based individual sites, but how do you scale it? I'm more interested in the scalability of this. If we ever get there, I don't know.
I have one follow-up
Please.
question. So the number you were using was 2.5, right? And that's, you're assuming that the effects of no-till and cover cropping are additive.
Correct.
Like, is there support for that? I haven't seen that. And the number itself seems really large compared to like other sort of natural climate solutions papers that I've seen.
Yeah, good point. I think that was just a sort of logistical answer, logical answer that I came up with. But I agree that they may not be cumulative, that it may be half of that, right? And you would have to double all the years that I mentioned.
Yeah.
Yeah.
Yeah, I'm curious about your spatial resolution of your satellite image, because I saw it was at a very fine scale, right?
These are all at 10-meter resolution.
Oh,
Yeah.
just from the Sentinel-2, right?
Correct.
Yeah,
Correct. And Sentinel-1 as well.
Sentinel-1, yeah, and there comes a question that each July ring has a diameter of 25 meters, and for each July ring, it might contain several pixels, right? And also, there's an uncertainty for each July ring's geolocation. It
Correct.
is about 10 meters, so
Correct.
there might be a drift for the location, so it might bring some concerns when you just making up the training data set for the July.
Correct. So the JEDI above ground biomass estimates have been screened by quality flags, but they were not screened by that spatial shift.
Yeah.
And then what I did is I simply sort of made everything at 25-meter resolution. I mean, across those inputs, they're not all 25 meters. And you know, in some cases it was the mean, et cetera, et cetera. But good point.
Do your results suggest that we should look favorably at increased agricultural intensity, like more plants per acre, because then there would be less of a need to take down forest?
Do you mean increase yield so that we don't have to expand the area?
Yeah, so for instance, like Iowa, it's been shown Iowa cornfields, you know, a lot more, maybe twice as many plants per acre now than there used to be. You know, you could get the same yield or more, even with the same amount or smaller plots of land. Do your results suggest that that's a good strategy because it would mean preserving more forest land and still get the same or better yields from crops?
To be honest, I don't think my results say anything about that. I mean, yeah, I do a lot of crop yield estimation for remote sensing. I deal with a lot of crop yield, and what I see is that, you know, there's certainly increases. There's an annual increase. You know, we all use sort of trend numbers, and they're different across the landscape. I think one of the sort of newer findings, if you look at the US data, is that there's a bit of stagnation of that increase. That, you know, we may have been gone, let's say, you know, X% every year, but there's a slowing down. I don't know what that means to the answer to the question that you're asking. I have seen sort of yield contests where people have produced 300 bushels of corn. Sorry, I've switched between empirical, not empirical, what is that, imperial and,
Metric.
and metric. But I always question them because at what expense did you produce the 300 bushels, right? They never say, they never talk about the other side of the equation, right? Is it twice as much fertilizer? Probably not, but you know, I don't know. I mean, I don't think we're anywhere there. I don't think we are anywhere sort of at a place where we can double the yields. I don't think we're anywhere near that, in my opinion.
Yep. So you mentioned at the end, and I think this is future work, some perhaps time varying component here. So I'm wondering if you can talk about that just a little bit more. So you did mention, you know, the expansion of agriculture, maybe somewhat at the expense of forest, but maybe more at the expense of grassland. So what would a time varying component, how would that work? And then what does that allow you to kind of address if you have that information?
I mean, on the forest side, it would be more like decades, right? You know, I think that's one of the reasons, if you look at the sort of literature, it says leave the forest alone, expand grassland, because there is faster turnaround, and then keep the croplands, but do all the regenerative sort of processes as you can. My results sort of support that. So for us, forest type would be decades. When I said time component, you know, one of the questions that I'm interested in is, you know, let's say that number is 2 or 1, whatever the number is in terms of soil sequestration. Is there a increasing returns? For example, if you did 5 years of regenerative practices, do you accumulate at 1 ton per hectare per year, or do you go up to 1.1, 1.2? If you look at the literature out there, most of them are very small time horizon, because it takes a long time to do these things. So there are a few papers where they looked at long time, but you know, they show up as one number in our review.
Yeah, thanks. And I'll ask one more too, if I can. So certainly there is some, I shouldn't use that word, there is uncertainty associated with this, right? And you mentioned it, and you even showed like, you know, plus minus 5 years. What part of the process are you getting those uncertainty bounds from, or what's causing that
Sure.
uncertainty?
Part of it is JEDI estimates. I mentioned about 20% root mean square error. The soil estimates, you know, there's an error bar, not error bar, but variation. So one of the things that I like to do, you know, in the next iteration of this is that, you know, put numbers and put some sort of error bars around them. But that's how I came up with 5 years.
Okay.
Yeah.
Thank you.
Did you have a question? Okay.
Other questions for Mutlu?
I'm happy to share my presentation. If you
I
want to
was
ask
gonna
questions
say,
later.
yeah. Overloaded.
You're fine.
Yeah. We'll take you when we can.
Yeah.
Okay. Well, let's thank Mutlu one more time. Thank you.